Hello, my name is Abiodun Hanifoshe. Today we're going to be talking about the last class on alcohol chemistry. Last time we talked about the oxidation of alcohols. Today we're going to be talking about the other reactions of alcohols, and we're going to be starting with the substitution to alkyl halides. So we're going to start with basically the nucleophilic substitution unimolecular, and that is SN1 reaction. So basically in this aspect of alcohol reactions, we're going to be talking about two kinds of reactions: nucleophilic substitution bimolecular, and that is SN2 reaction. So let's take a look at this we're going to look at the SN1 reaction first. So let's say we have something like this. This is a tertiary alcohol and it's butanol. We can convert this to a tertiary alkyl halide like this using HBr. So this is possible because this compound, this alcohol, tertiary alcohol, can give us this intermediate, which is a carbocation. This is a carbocation. So this carbocation is stable, and that is why the reaction between this and this to form this is an SN1 reaction, nucleophilic substitution unimolecular. So it's an SN1 reaction because this carbocation is first generated and the Br3. So basically we have something like this. So we have this generated, and then we have Br minus, which is the bromide ion, attacks this to form this product. So that is why we say this is an SN1 reaction, because the reaction happened at different times. So we have carbocation first, and then we have the nucleophilic attack of the bromide ion on the carbocation, and the other part of it is the, so let me show you the mechanism. Let's quickly look at the mechanism of the reaction. So we have something like this. This is our alcohol, butanol in this case, reacting with HBr. So basically the lone pair of electrons on the oxygen is able to attack this, and this is able to pick the electron to itself, such that we have something like this. And we have Br minus, and we're gonna have, let me write it like this. We're gonna have, okay, that's fine. We can write it like this, and then this is going to generate the carbocation by losing one molecule of water. So we have something like this, and the Br minus is going to basically attack this to form the products, and that is SN1 reaction, because the two steps happen at different times. We first formed the carbocation, and then we have the SN1 reaction, SN1 nucleophilic substitution nucleophilic unimolecular attack. So that's how that happens, and that is how we are able to form an alkyl halide, in this case alkyl bromide, in starting from alcohol. So we're going to see another example with a primary. So that was a tertiary alcohol. We're going to see another example with a primary and a secondary alcohol, but we're just going to use maybe just primary alcohol. So we can do this reaction with HBr so that we have this. But in this case, the reaction is going to, the nucleophilic substitution is going to happen concurrently. And that means that we're not going to form this species. We're not going to form this species because this species is not stable. Not stable. This species is not stable. Not stable. Hence, not SN, we can say hence SN1 not possible. So how then are we going to form this product from using this reaction? We are going to use an SN2 mechanism, and that is going to be something like this. We're going to have this attack is still going to take place. It's still going to take place because bromine is really electronegative. So then we're going to have this. And we're going to have this plus Br minus. But then the Br minus is going to come, attack this carbon. At the same time, the OH is leaving as water molecule. So we're going to have something like this. Oh, sorry, not the starting material again. We're going to have this, our propyl bromide plus water in this case. So this is SN2 reaction. So this is SN2 reaction because we're starting with a primary. So if we start with a primary alcohol or a secondary alcohol, we're going to be mostly considering SN2 reaction. But if we start with a tertiary alcohol, we're going to be, that is going to be an SN1 reaction. So this is going to be an SN2 reaction, starting with primary alcohol or secondary alcohol to give us alkyl halide is going to be SN2 reaction. So we can also, okay, one point to note is that if we are going to form alkyl chloride, say something like this, from an alcohol, we're probably going to be using zinc chloride together with the HCl, so that it can make our OH a good leaving group. So if we have something like this, we will need a zinc chloride. The zinc cation is needed, and we need HCl to form this. So basically, this is going to chelate with the oxygen so that we have something like this. Plus, and we have this chloride ion from the hydrogen chloride gas come attack this, and then this leaves. So basically we can form our zinc chloride that way. And we can also form, we don't really need to use this all the time, or maybe HBr all the time. We can also use some reagents like thionyl chloride and maybe PBr3 actually, phosphorus tribromide. So we can use these reagents to also make alkyl halides starting from alcohols. So we're going to quickly look at that now. So if we start with, let's stick to this propyl alcohol. If we start with this, in the presence of thionyl chloride with pyrimidine, we're going to have this. And how does that happen? So this is thionyl chloride. Oh, let me draw it well. So this is thionyl chloride. Basically SOCl2. So we're having the propyl alcohol. So this is going to attack this. This goes here. So we form this. We form this. And then this comes back and this leaves. So we form this. Let me draw it here. So we form this. And so we form this. Let me erase this so it doesn't get in our way. So we form this, and then the pyrimidine, which is basically the pyridine, which is basically a base, comes to deprotonate this. So the pyridine basically takes this hydrogen away, and then this goes like this. So we form this. And then the chloride ion that left at this step comes back to attack this in an SN2 reaction, or we say SN2 steps, so that this goes like this and this leaves. So we form this. We form our product basically, plus SO2 plus, we form this plus SO2 plus, we have HCl. So we form an alkyl chloride, starting from alkyl alcohol, basically alcohol. We form from propyl alcohol, we're able to form propyl chloride. So the last example I'm going to look at in the conversion of alcohol to alkyl halide is the example that is going to utilize phosphorus tribromide. So let's say we have this, we want to convert it to this. We can throw in phosphorus tribromide, and we'll get this. So basically that reaction is as easy as the thionyl chloride example. So we're going to have something like this, and then we have PBr like this. PBr. So basically this is going to attack this, and this is going to leave. It's a very good leaving group. So we have this, we form this, And this whole thing here, it's a great leaving group. So the bromide that left is going to come back and attack this, and we're going to have this basically just go like this. So we have this, we have the products plus HOPBr2 as the byproducts. So that is how we've been able to form an alkyl bromide from PBr3 as a reagent. So to summarize this part, I'll just say we've converted alcohols to alkyl halide. And you know, alkyl halide can just be shortened to this, while alcohols can be shortened to this. So to do this transformation, we have used this reagent. So you can use either this. So we're instead of writing hydrogen chloride gas or hydrogen bromide gas, so we're just going to say hydrogen halide, which is represented by HX. So we have used this. So let me write it underneath. So we have used this reagent. So you can use this, or you use, in the case of forming alkyl chloride, we use this HX with zinc chloride. You can say HCl in this case. And then we've used this, and we've used this. So we are not using all of them together. So we can use any one of them. So using any one of them, any of these. And to summarize, we can do this. Also, if we start with a tertiary alcohol to alkyl halide, we said that would be an SN1 reaction. But if we start with a primary alcohol or a secondary alcohol to alkyl halide, we say that will be an SN2 reaction. So that is a summary of the reaction of alcohols with hydrogen halide, thionyl chloride, and phosphorus tribromide to form alkyl halide. Basically, the substitution reaction of alcohols to form the alkyl halides. So that is the summary. And next, we're going to jump into the dehydration to alkenes, reaction of alcohols that leads to the formation of alkenes. So I'll jump into that just in a moment. So in the last example, we talked about how alcohols can be converted to alkyl halide. In this example, we're going to see how we can convert alcohols to alkene. And this reaction will require a very strong acid and probably with heat. So we're going to have something like this. So we're going to still use this as an example, a tertiary alcohol. So if we react this with, let's say, H2SO4 in the presence of heat, we can form something like this. We can form something like this, plus water, which is basically an E2 product. It's an elimination reaction. So if we, dehydration to alkanes basically, but it happens through E2 elimination. So the mechanism of this would be something like this. So we have the tertiary alcohol. So in the presence of so let's say strong acid, so we'll denote the strong acid with this. And basically a protonated water, so it's used to denote strong acid in this case. So basically this attacks this, and this go back to the oxygen to form this. And the water can then leave. This group is a good leaving group basically, so it can leave, so that we have this. We have this carbocation. So we are still forming this carbocation in this case, but you know we are not having HBr. If we had HBr, we could have do an SN2 reaction to form an acute halide. So that's not happening here. So what we're going to have is this. Oh Lord. So what we're going to have is this. The water molecule is going to, so let's redraw this structure here. So you know that all these points here they are basically CH3. So we can redraw this whole thing like this. CH3, CH3, CH3. So there are 3 hydrogen atoms attached to each of the carbon atoms. So this is the same thing as this. We're just drawing it out so we can see what it's made up of. And there's a carbon here too. So I'm just going to use one of the hydrogen atoms. So I'm going to suppress the other hydrogen atoms just so we see how this elimination reaction is happening. So we're going to redraw it again. So this same thing here is going to go through this reaction. So we're going to bring one of the we're basically just showing one of the hydrogen atoms that is attached, the atoms that are attached to this carbon. So the water molecule is going to come again. We are using water, but it's basically, this reaction is happening in acidic condition. So it's going to pick this proton, and then this is going to go like this. So we form the elimination products. So we form these products, and that is our final product. So that's how we can dehydrate alcohols to alkene. And I'm going to look at another example, which is pretty much similar to this one. So it's just that we can form 2 different products. If we start with the example I'm drawing now. So if we have, let's say we have something like this, and then we subject this to strong acid plus heat, we can form these 2 products. The major product and this. So this is major product, and this is the minor product. The minor product. This is major product. And that is because one of the routes is going through an E1 mechanism. E1, which is so it is this one basically. So this is E1, this is going through E1 mechanism, and this is going through E2 mechanism. So this is basically going to follow the mechanism I just cleaned of the board. It's going to be something like this. We're gonna have something like this. Attacks this, goes here, so we form this. And then the water leaves, so we form this. We form this, that is minus water. And remember I said at this point, so we have 2 hydrogen atoms there, 2 hydrogen atoms there, 2 hydrogen atoms, 2 hydrogen atoms, 2 hydrogen atoms. At this point, if we have a terminal alkyl group, so it's basically having a 3 hydrogen atoms. So it's having 3 hydrogen atoms, sorry. So in this case, so we're going to just look at one of the hydrogen atoms. So we have option of removing this hydrogen or this hydrogen, but the most stable product is going to be the one that is going to lead us to the most stable product is going to be formed from the route that is most stable, basically. So we're going to, and the route that will give us the most stable product is going to be the route that will give us the most substituted alkyl compound. So, and the most substituted alkyl product is going to be this one. The less substituted alkyl product is going to be this one. This is less substituted because it's having, you can see we have a terminal alkene. When we have a terminal alkene, for sure that is less substituted. We don't want to have too many hydrogen atoms, you know. But in this case, we have 1 hydrogen atom attached to the carbon. Here we have 2 hydrogen atoms. Here we have a methyl group attached to the alkene functionality. So basically we're saying that this is much more substituted than this one, and that is why this route is going to be favored, and that is why it's the major products in this kind of reaction. And yeah, it's going through an E1 elimination, so it's going to be this proton that will be ejected, and that will be our water is coming again. Pick this proton, this go like this, so we'll form this product, and that is it. So that is how dehydration of alcohol happens. Alcohols can also be converted to alkanes, and I'm going to discuss 2 methods that we can use to accomplish that transformation. So the first will be dehydrating the alcohol to form alkene, and then subjecting the alkene to hydrogenation in the presence of platinum catalyst to form the alkane. And I already discussed how we can do a dehydration reaction in the previous reaction of alcohol that I talked about. So the second method would be to subject the alcohol to convert the alcohol to tosylate. So we have something like this. So this is in the presence of tosyl chloride. So tosyl chloride is this basically. So you convert this OH to this. So this is a very good leaving group. That's why we're converting the OH to this. And then the second step of in this method is to do a reduction using lithium aluminum hydride, so that we have this. So the lithium aluminum hydride is able to generate hydride ion, which can attack nucleophilically attack this, and this very good leaving group leaves, so that we form the alkane, which is C3 C3H8. So we form the alkane. You remember the formula for alkane, CnH2n plus 2. So this is the corresponding alkane that is coming out from the from this method. We first activated the OH and then reduced it to alkane. And so those are the methods, I mean, just two examples that we can use of two examples of reactions that we can use to convert alcohols to alkane. So the next one I'll discuss is the esterification reactions. The next reaction that I'm going to be talking about is the reaction between alcohol and carboxylic acid. And that reaction is usually catalyzed by sulfuric acid. So if we have something like this, reacts with carboxylic acid, we can usually form ester. So this is an ester, and this is alcohol. This is our carboxylic acid. So this reaction is often catalyzed by sulfuric acid. So how does this happen? So let's take a look at one example. This reaction is an equilibrium reaction, and let's say we have something like this. So if we protonate this in the presence of sulfuric acid, we're going to have, so we can either have this or we have this. Actually, we're going to have both of them at the same time, both of this. So it's an equilibrium reaction, and these two are in resonance. So we can have this. So once this is formed, that is the alcohol, the carboxylic acid has been protonated. So we're going to have the alcohol is going to basically attack the carbon here, and this is going to go this way. So we're going to have something like this. Let's put a star here to indicate that this alkyl group is different from the carboxylic acid alkyl group. So we're going to have something like this. I will just put this. So we have this. So once this is formed, oh sorry, this is wrong. We're going to have this. So these are all in equilibrium basically. So once this is formed, this can tautomerize with this. We can have this. Let me clean this part. And then we can have, so once this is formed, this can go like this, and this leaves as water. So we have this. That is minus H2O. So then, because this is in acidic condition, the water can then come again and pick this proton so that this can be neutralized. So we have this. Let me draw it here. We have this, which is our final product. Yeah, plus water, and that is minus H plus. So that is how we can convert alcohols to esters. So basically, alcohols react with carboxylic acid to form ester, and that is how the reaction happens. It's an equilibrium reaction. So next, I'm going to quickly talk about, before I leave the esterification reaction, I'm going to quickly talk about how alcohols can react with acid chloride. So we can also have alcohols react with acid chloride, and this reaction is actually easy. So if we have acid chloride react with alcohol, it's going to give us ester plus HCl. So basically we just have the alcohol like this, a nucleophilic attack, and I can just move it back to this place, but that's not the right way to do it. We are supposed to do it in steps, so that this go like this, and then it goes like this. It goes on the electron goes on the oxygen, and then it kind of stays there as an intermediate before so it forms an intermediate. Then the electron then comes back, and then the chlorine atom leaves as chloride ion, so that we have the final products. Let me just write it. It's not good to do chemistry like this, so let me just do it the right way. So we have this. When we have this attack, we form this. And then this comes back and this leaves. So we have this. And the chloride ion can then pick up the hydrogen atom, and this can neutralize this. So we form the final product. So that is how we can also convert acid chlorides to ester, to carboxylic ester, using alcohols. So the next one that I'm going to be discussing is the Williamson Ether synthesis, and I will do that just in a moment. Lastly, we're going to talk about how alcohols can be used to make ethers in what is known as the Williamson Ether synthesis. Basically, in organic chemistry, when we talk about ethers, we are talking about this group here. So this is the formula for ethers, and we're saying that we can make ethers using the reaction of alcohols with basically with alkyl halide. So when we react alcohols with alkyl halide, we're going to actually the reaction is in two steps. So we're going to first form what we call alkoxide ion. So the alkoxide ion is then going to react with the alkyl halide to form ethers. to form ethers. So let me quickly show you how that happens. If you remember in our, I think that should be the second class, the acidity of alcohols, we talked about the fact that alcohols can mostly be deprotonated using sodium hydride. So we can deprotonate this so that we can have an alkoxide. So this alkoxide can then react with, so we can put the sodium ion there to balance the ions. So this alkoxide can then attack the, let's have a primary alkyl halide here. Let's say ethyl bromide. So this alkoxide can then attack this, and the bromine atom leaves, is a good leaving group, so that we form this. We form this. So let me just draw a typical example now, and not just alkyl groups. So let's say we have this. Oh no. Let's say we have this ethanol basically. So we deprotonate ethanol with sodium hydride. We form this. We form this, and then this reacts with let's say ethyl bromide again. So this does a nucleophilic attack on this and displaces the bromine atom. So we form this plus sodium bromide. So this is basically is an SN2 displacement reaction. It's an SN2 displacement reaction. So we can see there's a back attack on the ethyl bromide, and that is why for the Williamson Ether synthesis we often use primary alkyl halide. Primary alkyl halide to aid the back attack. If we use a secondary alkyl halide or a tertiary alkyl halide, the alkoxide is going to act as a base, and that will lead to instead of us having an SN2 displacement, that is going to lead to an elimination reaction. And so that is how we use the alcohol's reaction with alkyl halides to form ethers in the Williamson Ether synthesis. And so this is the end of alcohol chemistry. By next week, we're going to be starting a new topic. And you can suggest new topics that I should talk about. But if I don't get any suggestion, I'm going to dive into a fresh topic in organic chemistry, and we'll see how we go from there. Thank you, and I'll see you in the next lecture. Bye.